To start with today, I wanted to reiterate some of the things we've already been talking about on the basic refrigerant circuit. We're also going to do a review of electrical terms. I like this piece of equipment because it gives you a visualization of refrigerant moving through the equipment, and everything's laid out so that we can actually trace our way through the equipment. And so we're going to go through and do that. But before we do, there's a really interesting characteristic of this trainer, which is that it runs R123 refrigerant. So if you look here on the screen, we're going to look at what our standing pressure or our static pressure. Static just means with the system off, refrigerant's not moving. So when we say dynamic pressures, that means when the system is running. When refrigerant is moving, when we say static pressure, that means when the equipment's off. Okay, you all buy that? You buy what I'm selling?
For $1.
Okay, good. For the right price. All right, so we're just going to compare and see if it matches up with the PT chart. So we've got the refrigerant slider app up from Danfoss, and I'm measuring the temperature here. So we got 81.6, so I'm going to enter that in, 81.6 into refrigerant slider. Because this is a single component refrigerant, we don't have any glide. We're on gauge pressure. We want to make sure we're on gauge pressure, not absolute pressure. You got that toggle there. Everybody see that? Okay, so we're on gauge pressure. 81.6 should be negative 0.14 psi. And if we look at this right here, I mean, we're right in there. These big gauges here are reading right about 0, maybe a little over 0. But again, this thermometer, you know, plus or minus 3 degrees is all I'm going to expect out of this. So let's go ahead and just plug this in and see what we get. So if we're measuring, we're going to say this is reading half a psi, so 0.5 psi. That's showing 83.75 degrees Fahrenheit. So we're close enough to say, all right, this is R123 in this system. So when you look and you see this liquid that's inside our low pressure float receiver or inside our high pressure liquid receiver, you're seeing refrigerant. You're seeing liquid refrigerant. But one of the things that you have to know about this piece of equipment is that it really isn't designed to show real refrigeration effect. It doesn't move much heat. So yeah, you got a compressor on it. Yeah, you got all the metering device. You got an evaporator, you got a condenser, but it's not going to move much heat. The reason they use R123 is because it is so low pressure. As you can see, at standing pressure, kind of what we would expect, you're right about atmospheric. And so you can use all this glass because you don't run the risk of exploding it with high pressure. One thing that we also have to consider is that because it's R123 and R123 is a B refrigerant, which is a toxic refrigerant, it's a good thing we don't have high pressure. If one of you smashed one of these tubes or something, we would all need to evacuate because this is again, we're right here by the big open door here, so it'd be easy to do, but it is a toxic refrigerant. Now this holds a very small amount of refrigerant. I'm not sure if it says right here on the face, we can find that later, but it is a very small amount of refrigerant, so it's, you know, it's designed for this application. But if it did leak, we would want to evacuate. In terms of running pressures, we're not going to see it change much off of that atmospheric. So at most, we may see 10 psi on the high side on this thing. Again, making it safe to use with glass tubing. We're going to go through the circuit one component at a time and just kind of show the operation. So in order to start it up, first I'm going to turn the fans on. So this one that I just turned on is the evaporator fan. I'm going to turn on the condenser fan, and now we're going to turn on the compressor. And the compressor has a digital control where we can actually this isn't the control. This is just a meter that we can see consumption in terms of both wattage and amperage, as well as monitor the voltage. So we have 120 volts. Our compressor is drawing 8.5 amps, a total of 467 watts, something like that. So let's start at the compressor and work our way through the circuit. And I'm going to rely on you to call out the different components and what's in them. This is kind of going to serve as our review of the basic refrigerant circuit in addition to being a review of this particular trainer and how it works. So we got our compressor. What's the primary role of the compressor? Pressure increaser. But when it increases pressure on the high side, what happens to the pressure on the low side? Decreases, yeah, so it drops. We call it the pressure increaser. It raises the pressure on the high side, but then it drops the pressure on this line entering the compressor, which is called what? It's the discharge line, right. It's discharging out of the compressor. And again, just as kind of a testament to the fact that this thing isn't doing a lot of refrigeration effect, when I feel these, there's not a huge temperature difference, right? But under normal conditions, what would we expect the temperature in this to be from just a qualitative standpoint? Like, what would we expect to see in this discharge line? 165 degrees is a common temperature in air conditioning applications that we see on a discharge line under normal ambient conditions, but in general we would say that it is high temperature. So we want to keep the discharge line cool if possible. If you're in grocery applications, one of the measurements you should be doing all the time is measuring your discharge line temperature 6 inches outside of your compressor to make sure that it doesn't exceed. The specifications vary depending on compressor type, but in general you don't want to exceed 225 degrees. There, that's sort of your high limit. Once you get to the point where inside the compressor head, your temperature inside your compressor head exceeds 300 degrees, you're going to start to get severe oil breakdown. Varies based on application, oil type, a few different things, but those are good general guidelines. What is the state of the refrigerant in the discharge line? Vapor. Vapor. What would happen if it was liquid? Yeah, it ain't going to be liquid. If there is liquid coming out of the discharge line, that means you're actually pumping liquid through the head, and that would be seriously no bueno. You know, we've talked about this before, while technically liquid is compressible, it's incompressible from a practical standpoint. And so within a compressor, you're just going to blow the thing apart. Now, scroll compressors, like we talked about, have that compliance where they can move and actually allow some liquid to travel through by unseating, so it helps prevent them from killing themselves. But with a traditional hermetic piston style reciprocating compressor, if you got liquid in that thing down the suction line into the actual head of the compressor in the compression chamber, you would damage it severely. Let's just pause here and look quickly at what we're looking at in terms of pressures. We've got compressor discharge, which is tapped right into our discharge line of just right at about 6 psi, and our compressor suction is just slightly below atmospheric, slightly below 0. Looking at it here, we'll say it's about negative 0.5. and our discharge is 6. You can see we didn't get a big swing in pressures there. This thing's not doing a lot of refrigerating. If you look at that on a PT chart, and let's do that quickly. Let's look at negative 0.5 on a PT chart. We'll just kind of stop there. We're still at about like 80 degrees. So we're running about an 80 degree evaporator coil. You're not doing much by way of refrigeration there. Now it may be how we have, and we'll look at this, it may be how the metering devices are set, but not a whole lot going on. But let's keep going through the circuit. We got our discharge line here, which should be fully vapor, travels up in here. We got this that taps into our discharge line. So what is this? Pressure switch. Specifically, what kind of pressure switch? High pressure switch, right? Because it's in the discharge line. Discharge line is on the high side of the system, and so this would be set to prevent an overpressure condition that would damage the piece of equipment. We're going to go up our discharge line, and then we reach this little guy right here. What is this? Reversing valve. This says reverse cycle valve on it. Old school term, they would call it a 4-way valve, but this is what makes a heat pump a heat pump. We're currently in cooling mode, at least we should be. We wanted to make sure, because this says that this is the condenser, we would just make sure that we had the same temperature here and here, and the same temperature here and here, and sure enough, we're in cooling mode. If I switch it, which I can do with this key right here, then we can switch it over. Now, it says right here in the instructions that we are never to operate the reverse cycle valve unless the discharge pressure is at least 15 psi, which that's getting up there in terms of this is the system's operating range. So we would have to intentionally make sure that we get our discharge pressure up before we try to shift the valve. And why is that?
It's based on pressure.
Because the valve shifts based on pressure, right? It's actually these pilot tubes that switch the valve. The solenoid only switches the pilot tubes themselves, and it's actually the pressure differential from the compressor that slides that canoe like we talked about on the inside of that valve. So if you don't have enough pressure differential, you don't have enough compression, a reversing valve's not going to shift. And for those of you that work in heat pumps, that's a common mistake. People condemn valves because they're not shifting when it's not the valve's fault. The valve requires pressure differential in order to shift. All right, so we come through our reversing valve, and now we go down this line, which is still our discharge line, and we go into the top of, what's this called? Condenser. And why do we go into the top? Because as it condenses, the liquid falls down to the bottom and it creates a liquid seal. That's the design, right? Then we come out of our condenser, and right now I'm not seeing much going on in terms of well, yeah, there is a little bit. You can see here it's fully vapor going in at first, and then we get a little bit of liquid down to the bottom of the tubing. Kind of hard to see here, but there's a little bit of liquid coming out of the bottom. And again, if this were a receiver or a condenser that we see in typical air conditioning, you would see a full line of liquid coming out of the bottom of this. And that's what we call our subcooling loop. So it goes in as fully vapor, and it comes out as fully liquid, and in between is called what? Saturation, right, or the condensing portion of the condenser. That's where it's actually doing the state change. So initially when it goes in, that's the desuperheating loop. Drops the temperature down to the saturation temperature, then it fully changes state, and then the subcooling. In this case, we're never reaching subcooling. So now we're going out of our condenser, out of the bottom of our condenser, and now we're going into this guy right here. And what is this? This is the receiver. So this collects liquid, and we can see we do have some liquid dumping in here. Then we're drawing out of the bottom of our receiver. Now, first, let's pause here real quick. Where is the receiver located on your typical residential air conditioner? You don't have a receiver in your typical residential air conditioner. You see receivers, larger refrigeration, larger systems. That's where you're typically going to see it. And it acts as kind of a buffer for refrigerant, so that way you always have good liquid quality going out. We say liquid quality, full liquid going out to your expansion valves or metering devices. It also acts as a storage tank, so that way you can have additional standby refrigerant. And rack refrigeration, that's huge, because it really varies how much refrigerant you need depending on how many cases are calling. It gives you that extra kind of buffer, so that way you can either have more refrigerant in the tank or more refrigerant out in the system. So we come out here, and the way I have these valves set right now, I have this guy shut off, and I have this guy here open. This I need to, yeah, okay, I have this guy here open. It's going in here. What is this right here? Liquid line filter dryer, right. And what does the liquid line filter dryer do? Catches contaminants, and it helps dry the refrigerant. It does not deal with non-condensables. I heard somebody say non-condensables. It does not deal with non-condensable gases. Non-condensables, by their very nature, are gases. Is a solid a non-condensable? Is dirt a non-condensable? No. Dirt's dirt. Dirt's a solid particulate. Non-condensable means a gas that won't condense. In terms of non-condensables, what we're going to see most often are air and nitrogen. So then on this, we come out of here, out of our liquid receiver, out of the bottom, and that is where you come out because liquid's on the bottom. Out of our liquid receiver, we go through this valve here, and now we're actually going through a flow meter here, and this is kind of just a cool little visual indication. If I start to shut this down, I can actually see a ball. So right now our flow is very low because our expansion valve is feeding a very small amount of refrigerant. If I open this hand valve, I can feed a lot more refrigerant through that evaporator coil really quickly, and you can see that. So a hand expansion valve is nothing more than a metering device that I'm activating by, opening it up, and it essentially is bypassing our regular metering device, but I'm jumping ahead of myself. So what do we call this line that leaves the condenser or the receiver and goes to the metering device? Liquid line. What does the liquid line have in it? Liquid. What's the temperature of the liquid? Well, it varies, remember, so I'm not asking for a rule of thumb here as far as temperature. It's going to be above ambient temperature. Sometimes quite a bit, some all the way down to barely above ambient, but it will be above outdoor ambient temperature. Outdoor temperature. So we go through, we go into our, again, if this hand expansion valve is shut, we're going this direction, going into our thermostatic expansion valve or thermal expansion valve. What does the thermostatic expansion valve do? Creates a pressure drop. It's a type of what? Type of metering device, right? It's the pressure dropper, pressure decreaser. Oh, I forgot to ask you, what is my little name for the condenser? Heat rejector. It rejects heat. Now we're going in, we're dropping pressure. The line that comes out of our metering device, what do we call that? If there is one. Call it the expansion line. Some people call it the flash gas line. Some people call it I've heard them call it saturated liquid, or you hear all kinds of names. But when I was in school, I learned expansion line, so that's what I teach you. So you get to benefit from my misinformation. And in this line, we've got refrigerant at saturation, so it's beginning to boil in this line. And then it goes up and it feeds into the bottom of our evaporator, which is what do I call the evaporator? Heat absorber, yeah. So its job is to pick up heat. Now again, not a whole lot going on in this one, but we can see bubbles going up here, and you get more and more vapor the further it goes up. So it's doing something. But under normal circumstances, it might look like this at the beginning. There'd be a little bit more vapor than this, but at the end, we would be fully superheated, which would mean at the end of our evaporator, what's the state of the refrigerant? Vapor. It goes in at liquid at the bottom, Comes out at vapor to the top. Depending on how early in this evaporator it changes fully to vapor, that dictates how much superheat we have. I mean, that's a backwards way of saying that, but you get the point. If we fully boil off here, then I'm going to have a higher superheat up here than if we fully boil off here, and only that last row. So when we have high superheat, that means that we're not effectively using the whole evaporator coil. When we have low superheat or zero superheat, that means that we're running liquid too far through the evaporator coil. Overfeeding, right? That's another way of saying that, which could result in what? If we overfeed an evaporator coil, what can happen? Slugging, flooding, getting liquid back to the compressor. And as we talked about before, my grandpappy always told me, you should not get liquid back into your compressor. Actually, he never told me that, but he should have. You know, if he was a better grandfather. I have a lot of issues because of this. He forgot to tell me. All right, and so we go out of our evaporator coil. Now we go back into our reversing valve, which then directs it this direction. We're measuring our compressor suction here, which has continued to drop here. So we're starting to do a little bit more here. Our head pressure is 9 now, and our suction is about -2 PSI. So we got a little more going on. And now we're going down, and we're feeding back to our compressor again. Now this little guy right here, I shouldn't see any liquid in here. If I do, that means I got liquid going back to my compressor. Now I will see a little bit of something, and what is that I'm seeing traveling back? Oil. I do need to have some oil traveling back. If I don't, that's a problem. That refrigerant needs to be carrying some of that oil with it. And that's not because we necessarily want that, but it's just the nature of this type of equipment. Unless we have an oil management, like an oil separator or something like that, a decent amount of oil is going to make it into the system. And that refrigerant needs to carry it back. The ability for refrigerant to carry oil, we call that miscibility. So is the oil miscible in the refrigerant? Now, that is a broad term that we use. In fact, that's actually only talking about liquid in liquid in terms of the scientific term. But in the trade, when we say miscibility, we're basically saying how well does the oil mix with the refrigerant and how easily is it carried back. So when we see this little haze in the bottom of this tube, that's okay. Now, actually, I am seeing a little bit of surge of liquid every once in a while. And that may be because something's making it through the hand expansion valve, or it may be because the valve is overfeeding. But again, this valve is doing its job if it does what? I actually kind of skipped this a little bit, so I want to come back here. What is this? What is a expansion valve, a thermostatic expansion valve's method of metering refrigerant? Superheat. Superheat. It's a constant superheat valve. Now, it's not fully constant. My buddy Jamie Kitchen from Danfoss may watch this, and he gets crazy when people say that it's a constant superheat valve, because it's not completely constant. There is variation in terms of opening force, but it's fixed within a range, within its normal operating conditions. So this valve is going to throttle in order to maintain the superheat where? The suction line, right. Now, quick note, is this an internally or externally equalized valve? Well, you're going to notice there's no external equalizer. You've got a bulb and you got nothing else. Now, the reason this valve doesn't need to be an externally equalized valve is because there is next to no pressure drop across this evaporator. And why is there next to no pressure drop across this evaporator? Because it's got giant tubes on it and no fins, and there's almost nothing going on here, right? There's really, this is not really representative of what a real evaporator coil is like in terms of pressure drop. A real evaporator coil has many more rows. It has a distributor, a lot more things going on. And so this evaporator doesn't need an external equalizer because the pressure here is going to be pretty much the same as the pressure here. But in a real coil that we work on day in and day out, most of the systems we work on, there will be a significant difference, and that's why the valve has to be measuring the pressure or the closing force at the end of the evaporator coil, not just at the beginning. That makes sense? Because again, how do we measure superheat? We measure a temperature and a pressure at the outlet of the evaporator coil. I understand this is drinking from a fire hose kind of stuff here, but it's a review because we've already talked about almost all of this stuff. We haven't gotten very far into subcooling and superheat yet, so we're going to do a lot of reps on that. We're going to do a lot of connecting. We're not going to do connecting into this system. We're not going to take and hook up to our valve on this system. Do you know why? Well, it's a toxic refrigerant. We're not going to mess with a toxic refrigerant. We're just going to use the gauges on here. So this isn't going to be a system that we use for connecting gauges and dropping the charge and recovery and evacuation and all that. This is specifically for us to really ingrain the different components and to be able to visualize the refrigerant moving through the system. That is the purpose of this. Now, we are going to be able to do some diagnosis, actually check some things electrically. There'll be some of that, but as a review of the purpose of this trainer, the purpose of this trainer is for visualization purposes and for demonstration, because you can all see this thing, which is kind of cool. When we work on this little North Park trainer over here, this little tabletop guy, that's a much more realistic refrigeration unit. But you notice it's much smaller, and so it's hard for everybody to see what's going on.